Section 1. The Foundation, Understanding Binary Locks. Binary locks represent one of the most fundamental mechanisms for controlling concurrent access to data items in a database system. The core idea is straightforward. A data item can be in one of two states, either locked or unlocked. Think of it like a single key for a room. Only one person can hold the key and be inside at any given time. If a data item, let's call it X, is locked, its current lock value can be considered 1. Conversely, if item X is unlocked, its lock value is 0. This simple binary state is the basis for preventing conflicting operations from occurring simultaneously, which could otherwise lead to inconsistencies in the database. When a database transaction needs to access a data item, it must first request a lock on that item. This is typically done using an operation. If the data item X is currently unlocked, the transaction is granted the lock. Upon granting the lock, the system changes the lock value of X to 1, indicating that it is now in use. However, if another transaction already holds the lock on X, the requesting transaction cannot proceed immediately. It must wait until the item becomes available. This waiting mechanism is crucial for orderly access. The operations and its counterpart are critical and must be implemented as indivisible operations. Indivisibility, often referred to as atomicity, means that the operation must be performed in its entirety without interruption or not at all. For this ensures that checking the lock status and setting the lock occur as a single, uninterruptible step. Similarly, must release the lock cleanly. If a transaction requests a lock on an already locked item, the system typically places the transaction in a queue specifically for that item X. When the item is eventually unlocked, a transaction from the queue, often the one that has waited the longest, is granted the lock. A practical implementation of a binary lock for a data item X might involve a small record or data structure associated with X. This structure would usually contain fields such as the name of the data item itself, a variable to store its current state, and an identifier for the. Additionally, to manage waiting transactions, this structure would include a pointer or reference to a queue. This queue holds the list of transactions that are currently suspended, awaiting their turn to acquire the lock on data item X, ensuring a fair and orderly progression of operations. Section 2. Rules of Engagement for Binary Locks. To ensure that binary locks effectively maintain database consistency and prevent issues like lost updates or inconsistent reads, transactions must adhere to a strict set of rules. These rules govern how and when locks are acquired and released. The first fundamental rule is that a transaction must issue an operation before it attempts any or operation on the data item X. This prerequisite ensures that no access, whether for reading or modification, occurs on an item unless the transaction has exclusive control, as granted by the lock. This preemptive locking is the cornerstone of preventing simultaneous conflicting accesses. The second crucial rule dictates the timing of releasing a lock. A transaction must issue an operation only after all its and operations on that specific data item X are fully completed. Releasing a lock prematurely, while the transaction still intends to operate on the item, could allow another transaction to acquire the lock and modify the item, leading to inconsistencies or reading uncommitted data. Holding the lock until all operations on the item are finished ensures that the transaction sees a consistent state of that item for the duration of its interaction with it. A third rule prevents redundant locking by the same transaction. A transaction must not issue an operation if it already holds the lock on item X. While this might seem intuitive, enforcing it prevents unnecessary overhead and potential complications in the lock manager. If a transaction already has the key to the room, it doesn't need to ask for it again. Attempting to reacquire an already held lock could, in some implementations, lead to deadlocks or simply waste system resources processing a superfluous request. Finally, the fourth rule concerns the proper release of locks. A transaction must not issue an operation unless it actually holds the lock on item X. Attempting to unlock an item that is not locked by the requesting transaction or is locked by a different transaction is an erroneous operation. Such an action could inadvertently release a lock held by another valid transaction, thereby compromising data integrity and the entire concurrency control mechanism. These rules, when followed diligently by all transactions, create a disciplined environment for data access, significantly reducing the likelihood of concurrency-related anomalies. Section 3. enhancing concurrency, shared and exclusive locks. While binary locks are effective in ensuring exclusive access, they can be overly restrictive, especially in environments where many transactions primarily read data. If a data item is locked with a binary lock, no other transaction can access it, even if those other transactions only intend to read the data and not modify it. This limitation can unnecessarily reduce the level of concurrency, as multiple read operations could safely occur simultaneously without conflict. To address this, a more sophisticated locking scheme known as shared exclusive locks, or read-write locks, was developed to allow for greater parallelism. This enhanced locking mechanism distinguishes between two primary modes of access reading and writing. If a transaction T1 only needs to read a data item X, it can acquire a shared lock, often denoted as an S-lock or read lock, on X. The key property of shared locks is that multiple transactions can hold a shared lock on the same data item X concurrently. This means if T1, T2, and T3 all want to read X, they can all acquire shared locks and proceed simultaneously. This significantly improves throughput in read-heavy workloads, as readers do not block other readers. Conversely, if a transaction T2 needs to modify or write to a data item X, it must acquire an exclusive lock, often denoted as an X-lock or write lock, on X. An exclusive lock, as its name implies, cannot be shared. If a transaction holds an exclusive lock on X, no other transaction can acquire any lock on X, neither shared nor exclusive, until the exclusive lock is released. This ensures that a writer has sole access to the data item, preventing any other transaction from reading a partially modified state or writing to it simultaneously, which could lead to data corruption. The system uses three main operations for this scheme: to acquire a shared lock, to acquire an exclusive lock, and a common operation to release either type of lock. The decision to grant a lock request depends on the type of lock requested and the type of lock or locks already held on the item. This is governed by a lock compatibility matrix. For instance, if transaction T_A holds a shared lock on X, and transaction T_B requests a shared lock on X, TB's request can be granted. However, if T_A holds a shared lock and T_B requests an exclusive lock, T_B must wait. Similarly, if T_A holds an exclusive lock, any request from T_B, whether for a shared or exclusive lock, must wait. Section 4. A look into the past. Multi-version timestamp ordering. Traditional locking mechanisms, even shared exclusive locks, can sometimes lead to situations where transactions are blocked, waiting for locks to be released. This can limit concurrency, especially if long-running transactions hold locks on frequently accessed data. Multi-version concurrency control, or MVCC, techniques offer an alternative approach that aims to increase concurrency by allowing transactions to read older, consistent versions of data items while other transactions might be modifying newer versions. One prominent multi-version technique is based on timestamp ordering. In this scheme, the system maintains several historical versions of each data item X. Each version of a data item X is not just its value, it also carries important metadata. Specifically, each version stores its own value, which is the largest timestamp of any transaction that has successfully read this version, and which is the timestamp of the transaction that created or wrote this particular version. Timestamps are unique identifiers assigned to transactions, typically when they begin. These timestamps are used to order transactions and to determine which version of a data item a transaction should read, or if a write operation is permissible. The fundamental principle behind multi-version timestamp ordering is that a read operation by a transaction T can be satisfied by reading an older version of the data item, whose is appropriate relative to T's timestamp. This means that a read operation rarely needs to wait for a write operation to complete. If a transaction wants to write a new version, it can do so, and subsequent reads from other transactions can either see the new version or an older one, depending on their own timestamps. This allows for a scenario where readers do not block writers, and writers do not block readers, significantly enhancing concurrency. The use of timestamps provides a clear chronological order for operations. When a transaction T starts, it is assigned a unique timestamp. All concurrency control decisions for transaction T are then based on this timestamp. If the system perceives transaction T1 as being older than T2, it attempts to ensure that the execution schedule is equivalent to a serial schedule where T1 executes before T2. This ordering, combined with multiple versions, helps in resolving read-write and write-write conflicts without necessarily blocking transactions, though it might lead to transaction aborts if an operation violates the timestamp order. Section 5. Mechanics of time reading and writing in multi-version systems. In a multi-version system based on timestamp ordering, the procedures for handling read and write operations are quite specific, and rely heavily on the timestamps associated with transactions and data item versions. Let's first consider an operation issued by a transaction T. When T intends to write to data item X, the system attempts to create a new version of X, say xk plus 1. This new version will have it set to the timestamp of transaction T. Similarly, its will also be initialized to. This initialization reflects that T has both written and conceptually read this new version it created. However, this write operation is only allowed under certain conditions to maintain serializability. The system checks the existing versions of X. It finds the version, let's call it she, that has the highest that is less than or equal to. This she represents the latest version of X that was committed before or by a transaction with a timestamp no later than T's. The write by T is permitted only if is greater than. If is less than, it means some other transaction T, with, has already read version she and expects it to be the latest version relevant to T. Allowing T to write would invalidate this assumption, so T is aborted and typically restarted with a new, larger timestamp. Now let's examine the operation issued by transaction T. When T wants to read X, the system's goal is to find the most recent committed version of X that was written by a transaction whose timestamp is less than or equal to. So the algorithm searches among all versions of X to find the version she that has the highest such that. This ensures that T reads a version of X that was current or existed at the time, as per its timestamp. T began its relevant operations, upholding the consistency of the read. Once this appropriate version she is identified, its value is returned to transaction T. As part of this read operation, the system also updates the for the version she that was just read. The is set to the maximum of its current value and this update is crucial because it records that a transaction with timestamp has now read this version. This information will be used by subsequent write operations. As described earlier,